This is video 4 out of 4 for class 1. So in this video, I want to talk a little bit about some of the technologies we have at our disposal, why those technologies are here, and what they help us do. So we can think about this as having three main categories of technologies within our reach. The first type is what we use to store and manage data. The second type is what we use to analyze data. And the third type is what we use to visualize data. Now, when we talk about big data, all these components are important because we need to store and manage data, but ultimately that is for the purpose of analyzing it. And visualization is what we use to convey messages, to convince an audience that what the data says actually should drive our decisions and to help other people interpret the data in a manner that is intelligible for them. So in the past or in the current times in many organizations still, we really had one main technology to store and manage data, and that is what we call the Relational Database Management System, or RDBMS, so your Oracle, Sybase, DB2, Microsoft SQL Server, and whatnot. And of course, the overarching, ever-present system that we have in organizations, that is Excel. Excel is not known necessarily as a database, but it is known as an incredible repository for organizational data within organizations. So people might pull information from various sources in the organization in databases, but then they do very high number of manipulations of data within Excel, and a lot of the knowledge that we actually would need to capture when we're trying to leverage data is effectively embedded within Excel spreadsheets sometimes. Now, for analyzing data, one of the largest and most popular tools that has been used in larger organizations is called SAS. Now, SAS is a statistical software package that's been around for several decades now, and it really has taken hold in organizations because it provides a proprietary, yes, but very well-supported environment that a lot of statisticians and data scientists in large organizations, financial institutions, in retail, banking, travel, and a number of other areas are using. R is another product that's being used, but to some extent in traditional organizations, its use was actually fairly limited. And of course, Excel is one of our main tools for analyzing data. The last category for visualization involves crystal reports, business objects, and of course Excel again. So we have Excel everywhere here, and that is effectively the Swiss Army knife of the tools for data management and analysis. And this is pretty much the toolkit that you'd find in many organizations that are more on the traditional side of using data. When we talk about big data, we have an evolution really that takes place in that the relational databases are still very much in use, but we have other types of databases that we can use, such as document databases, graph databases, key value stores, column stores, etc. And the idea here is that different data structures, so when we talk about variety, for example, of data, will call for different types of systems to store and manage them. We also have multiple tools to analyze data. So SAS is still very much in use, but a lot of organizations are moving towards using R because it is open source, free, and very well supported by the open source community and used by statisticians in academia who often now work in organizations as well. Python, which is a general purpose programming language that has very good support for data analysis through a number of third-party libraries that are also free. Or some are commercial as well, but Python essentially has taken hold and is being used at companies such as Google, Microsoft, and a number of other large players to actually do artificial intelligence software or analytics software. We also have multiple tools to visualize data. So now Tableau, Power BI, and Business Objects and other products such as those are incredibly important in organizations because they help us do what we call data storytelling. So rather than looking at numbers and figures in tables or graphs, when we need to convey certain decisions that must be made and how data helps us make these decisions, we might use these tools to help convince an audience that is not primarily literate with a lot of data analysis techniques and it helps us convey the message better to the audience, and it really helps push the data closer to those who need to make the business decision. Now, the other advantage of these tools is that they help users get access to the data directly because they connect virtually to any number of sources that are at the disposal of the users. We also have an added factor that increases the types of offering we have. It's our ability to use things on premises and in the cloud. So in the past, all these systems that you were using, you had to install in your own servers, in your data center, and you had to maintain and manage them. Now, with cloud offerings, we can go on providers such as Google, Microsoft, or Amazon, and effectively start using these tools very quickly. If we have a credit card, of course, but we're able to get started very quickly to store and manage large quantities of data, to analyze large data sets, and to do visualization as well. So the advantage is really that we have the right tool for the job. We have a large offering that fits different needs, and based on our needs, we can get the best tool for the job. This is something we couldn't do before because we really had a couple of tools available, and they worked with our special use cases, but they were somewhat clunky and they didn't always work the way we wanted, but we made do with them. We also have incredible strides that have been made by open source software projects. So it's very important to think about this because open source has really driven big data in the past 5 or 10 years in terms of providing the support, but also providing the development of new products and the evolution of existing products. There's also no ramp-up time and elastic capacity when you talk about cloud offerings. So you are able to expand or contract your needs and really get started very quickly when you use cloud-based offerings as opposed to having things on premises in your data center where you first have to buy the hardware, install the operating system, and have everything done by the IT department that also has tons of other projects to manage. So that really has helped get things moving faster for organizations. Now, some of the disadvantages primarily include the fact that the complexity of the infrastructure is growing. You have the right tool for the job, but that might mean you have many tools which require different expertise to be used or to be managed. And sometimes some of these products are not necessarily very mature. So you have to be willing to live with different issues for a time while the product is under development if it's still not very mature. You also have a dependence on multiple providers. So if you have contracts with cloud providers, you have different systems in place, you have to be willing to depend on multiple providers, whereas in the past you had one vendor that was a sort of one-stop shop for everything you needed in terms of data management. You might also have to incur some rework and technical debt as some of the products that you use continuously evolve. The platforms that you use are changing fairly regularly, so there's less stability in terms of features and how you have to do things, but over time these get ironed out and then you eventually get in a relatively stable stage. The last point is an altered cost structure. So in the past you were buying equipment and you were amortizing it over a certain period of time. Now, when you do things on the cloud, you essentially rent capacity. And renting capacity is not the same as amortizing equipment. So in some organizations, that changes the way the accounting for managing data effectively works. And that can be a bit of an adaptation that's required within a certain environment. Now, why all of this matters? So what's important to remember here is that we're really changing the paradigm of how we work. In the past, when we had more data to manage, when we had data to manage that was coming in at a faster rate, we would do what we call vertical scaling. So vertical scaling is the fact that we take a computer, and if we need more capacity in the computer, we add capacity to that computer. Now, this is feasible up to a certain point. And what happens is for a while, you're able to increase the capacity of your computer. Eventually, you can buy a bigger computer altogether, increase its capacity as well. It's becoming more and more expensive, but it's still physically doable to increase the capacity of the computer. The problem is, at some point, you reach a certain limit, and the amount of data that you have to store and that you have to analyze and that you have to process will just not fit on a single computer, or will just take too long for a single computer to process and analyze for you to get a timely response. So this is where you move from having something that is economically feasible to something that is economically unfeasible because it's too expensive, to something where really it's physically unfeasible because you just are not able to do it with a single machine. And this is where adding capacity will not work anymore. And this is where you switch to what we call horizontal scaling. And a lot of big data technology is based on this idea that rather than increasing the capacity of a computer, you will just add more computers. And you will go from working with a single computer, which is effectively a single machine, to working with what we call a cluster, which is a group of computers that are working together to perform certain tasks. And when we talk about big data, we're really talking about the age of the cluster, because we're talking about clusters or groups of 10, 50, or 10,000 computers sometimes that need to work together to perform certain tasks together in parallel to get the results faster, to store larger quantities of data. So at a high level, we have the data that our operations generate, and we have to ingest this data. Once we have ingested it, we have to store it somewhere. Once we've stored it somewhere, we have to process it. Once we've processed it, we have to analyze it, and eventually this analysis will help us derive a certain output. And all these steps are required for us to really make the inference or help with the decision-making process that we have. Now, for each of these steps, we may need a different technology. So we have quite a complex infrastructure in place, as we've told before. One technology may cover multiple parts of this process, which is then fine because you have more economies of scale, or multiple technologies may manage part of each process. So when you do analysis, you might have a certain tool that does part of the analysis with another tool that does the second stage of the analysis, and finally a third tool that you use to visualize the output and present it to help the decision-making process. So what you have is really a fairly simple pipeline when you think about it conceptually, but from a technology perspective, it can be quite complex. Now, to give a couple of examples, we'll talk today about Apache Hadoop and Apache Spark. This will help us understand a bit better how computers work together in a cluster, but also contextualize the kinds of problems that these tools are used for nowadays. Now, both these tools are open source projects, and they have been adopted and sometimes customized by many cloud vendors. So the product called HD Insight on Microsoft Azure, which is Microsoft's cloud platform, is essentially based on Hadoop and has extensions that are managed by Microsoft to provide additional functionality. But the idea is that these projects, they're open source, but they drive a lot of the efforts that are being made in big data and a lot of the use cases of big data in organizations. So Hadoop is essentially a framework that allows you to perform what we call batch processing of large data sets. So batch processing is a logic we've discussed earlier where you take data at regular intervals and you process it. It is not built to treat data in real time. It is built to process a large amount of data at regular intervals. So for example, every day or every hour or every week or every month, rebuilding customer profiles for segmentation purposes, for targeted ads, or these kinds of things. One of the most important aspects of Hadoop is that it allows the developer to focus on what they're trying to do in terms of processing, but not have to worry about how the computers have to work together to do it faster. This is handled by the system itself. The developer just says, I would like to process all this data and do this operation with this data. Now, to do so, Hadoop has three main components. The first one is what we call a distributed file system, and essentially it means that all the computers working together in the cluster are sharing their storage capacity so that the user thinks that there is really one computer with one extremely large hard drive where the data can be stored. There's also MapReduce, which is a parallel programming framework. So it is essentially a way of programming operations that need to be done on the cluster, and the system will take care of making those operations be performed in parallel to get the result faster. So Hadoop essentially takes a large data set, splits it, and assigns parts of the task that the programmer wants to be done to machines within the cluster, who will then each report their results, and the results will be collated together as a single answer that will be reported back to the user. The last component is called Yarn, and it's essentially a component that manages how jobs are scheduled and negotiated among the resources within the cluster. So you have an orchestrator, you have something that treats the data, and you have something that stores the data. Now, this all worked very well, and it was used in many companies for the past 10 years, but there's been some criticisms of Hadoop, which is the fact that it is batch-oriented. One of the main criticisms of batch-oriented frameworks is that they do not allow for fast real-time processing. When we talk about velocity, we talk about the ability to react faster. So we need things to be able to happen in real time. And this is where products such as Apache Spark come in. Apache Spark is a framework that's made to perform analytics on large data sets. So it includes replication and fault tolerance so that in the event of a failure, things are restarted on their own, but it includes a lot of functionality to be able to work in real time. It does not deal with storing the data. It actually often uses Hadoop for that, but the processing part is managed much more in memory than with Hadoop, which primarily relies on hard drive storage, and that allows it to perform work a lot faster. What you see at the bottom right here is a little diagram that shows that I think it's a logistic regression computation task that is performed by Hadoop in 110 seconds and performed in 0.9 seconds by Spark. A lot of this optimization is done by having the data stored in memory as opposed to on disks, which is what Hadoop does. And what Spark has offered for organizations is really the ability to go faster and to work with high velocity data. And then what this does is it enables real-time processing and real-time decision making, for example, for artificial intelligence systems that must react in real time to events taking place. So that's it for this part. These are two of the tools that are very heavily used in the industry right now. The main idea is that these tools, like many other big data tools, work on clusters rather than single computers, and they are able to do horizontal scaling, which is that we can add machines to help with the workload rather than increasing the capacity of a single machine, because that is eventually too expensive or impossible to do. Thank you very much.